Greetings and welcome. Let's take a look at our first example problem. So first, I apologize if my writing's a little off. Got a new stylus because the last one broke, and hopefully it does the trick. So problem 1. Calculate the entropy change of steam between states P1 equals 36 bars, T1 is 250 degrees C, and P2 equals 22 bars, and T2 is 400 degrees C by direct application of the definition of entropy. Hint, devise a path of constant pressure followed by a path of constant volume that connects the two states. We can assume Cp is this value and Cv is that value. They're given as constants, so I guess I can assume that Cp and Cv are constant for our process, since we're not told or it's not suggested otherwise. Great, right? Entropy is a state function, right? So in theory, since my initial and final state are defined, since I know T and P in both, if that point was in my steam tables, I could just look up the value of entropy in the two states and compute the change in entropy as the difference. But here, it's suggesting that we construct a thermodynamic path from initial state to final state, calculate the change in entropy for each of those paths, and then we'll add them together to get the overall change. So let's do it. All right, so we have some initial state, state 1, where I have a temperature of 250 degrees C, and my pressure is 36 bars. Okay, and then I'm going to draw it over here. I'm going to have some final state in which my temperature is 400 degrees C, and my pressure is 22 bars. Okay, and then if I interpret the problem correctly, it says devise a path of constant pressure followed by a path of constant volume that connects the two states. Is I'm going to create an intermediate state. Okay, and so initially I'll be at T1 P1 in some volume V1. My final state will be at T2 P2, and I'll have some volume V2. Okay. And then I'll have some intermediate state, which is going to be at some temperature Ti, some pressure Pi, and some volume Vi. Okay. It says devise a path of constant pressure followed by a path of constant volume. Okay, so if I'm going from my initial state to my intermediate state and I have a path of constant pressure, that means that Pi will be equal to P1, which in this case is equal to 36 bars. And then a path of constant volume, that tells me that Vi will be equal to V2, since my second step or second path is going to be isochoric. So Vi equals V2, and V2 I don't know quite yet, and I don't know Ti yet. All right, so let's go to the steam tables. Let's see if we can figure out what states we have in my initial and final state. And then in order to solve this, so if I'm going to need to try and figure out what my intermediate temperature is, and I'll need to know what my final volume is, and that should be everything that I know, or everything that I need. Okay, so I have MATLAB open up here, and I have my steam tables open over here. So I'm going to start by, I'm going to scroll down to my superheated steam tables. Come on. Okay, let me rotate that table and zoom in a little bit. Okay, and let's try and figure out what we have. So our initial state's at 250 degrees C and a pressure of 36 bars. Okay, so is 36 bars on here? All right, just so happens 36 bar is on here. And we find at 36 bar, our saturation temperature is 244.19 degrees C. All right, so since our temperature of 250 degrees C is greater than the saturation temperature of 244.19, that tells me that I have a superheated vapor. Okay, and we'll get V here in a second. Well, actually, let's just get it because it just so happens we have a pressure of 36 bars, and we do have a temperature column of 250. So let me write down V, and then just for speculation, let me write down S as well, because if we have it for the final state, we can compute the change in S from the steam tables as for comparison. Okay, so V1, 250 degrees, C in 36 bars is 0.0568, 0.0568. And that's meters cubed per kilogram. And S, sorry, this stylus is a little touchy. So entropy down here, 6.1545. So 6.1545. And that'll be kilojoules per kilogram. Okay. And if we go to our final state, so our final state is at 22 bars. So 22 bars, our saturation temperature is 217.26. So since my temperature is greater than the corresponding saturation temperature at 22 bar, right, again, I'm going to have a superheated vapor. Right, and the temperature is much higher there. Let's have a superheated vapor again. So let's see. So at 22 bars, 400 degrees C is on here. So I can read off V at 0.1371. And that's meters cubed per kilogram. And let's just read off entropy, because again, we could, in theory, just use that to calculate the change in entropy. So 22 bars, 400 degrees C, 0.1371, and then entropy is 7.0813. 7.0813. Okay, and that's kilojoules per kilogram, and actually should be kilograms per kilogram, kilojoules per kilogram Kelvin. All right, kilojoules per kilogram Kelvin. All right, because S has the same units as R. It says kilojoules per kilogram Kelvin, kilojoules per kilogram Kelvin. All right, so now the significance of knowing V2 is now my intermediate state is known. Right, it's at 36 bars, and now we know the volume. I'm going to need to solve for the temperature. Reason being is, we're going to have to, perform integrations to calculate my change in entropy for those two steps. All right, so 36 bars. So you go back to the superheated steam tables. So 36 bars, please be on here. So we're at 36 bars. Okay, and now what I'm looking for is I know that my volume, okay, at this intermediate state, again, is equal to my final volume, which is 0.1371 meters cubed per kilogram. Okay, so what I'm looking for is at 36 bars, where I have 0.1371, and it actually looks like I'd be off the charts here. All right, we need 0.1371. Table ends at 800 degrees C, in which V is 0.1367. Right, so it looks like I would be just beyond 800. Right, so it'd be slightly off my charts. Well, since my steam table ends, right, I could, in theory, I suppose I could try and extrapolate, but you should always extrapolate with caution. And so since we're pretty close to the volume here, 800, I'm just going to take my temperature to be at 800 degrees C. Okay, so ideally we would have one more column here, and then I would interpolate between those 2 points. But it looks like we won't be very far from 800. Our steam table ends, so I'm just going to take it to be 800. Right? You could extrapolate, but again, we should be really close to this value at 800, since that's 0.1367. Here it's 0.1371. Okay, so I'm just going to say that Ti, right, is approximately equal to 800 degrees C. Again, I apologize. It's approximately equal to 800 degrees C. Okay, so let's go ahead, all right, and let's try and construct our process to compute the change in entropy, and going from state 1 to state 2. So we'll compute the change in entropy for our isobaric process to go from our initial state to our intermediate state, and then our isochoric state, so process of constant volume, or isochoric process, to go from our initial state to our final state, calculate the change in entropy, and then we can actually compare to the direct result from the steam tables. Okay. So first, let's look at state 1. Okay, 2, come on. From state 1 to our intermediate state. Okay, so we're going to go from 1 to state I. So this is an isobaric process. Boy, I am really apologizing about this stylus. So we haven't. Okay. All right. All right. So key is remember our first law of balance for an isobaric process. So if we have a process at constant pressure, from chapter 3, we found that our first law of balance reduced to delta H. Come on. Delta H was equal to Q, okay, which would be equal to, so delta H would be the integral of Cp dt. Okay, in this case, this would be from our initial state to our final state, which is that intermediate state. In differential form, we would have the dH, okay, is equal to dq, okay, and remember sometimes you get a curly differential to remind ourselves that q is a path function, and that would be equal to Cp dt. All right, so my definition of entropy is what? Is that ds is equal to dq reversible over t. Okay. So for my problem here, for my isobaric process, I would get that ds is equal to, well, dq for my isobaric process is dh, which is Cp dt. So it's going to be Cp over t dt. All right. So then my change in entropy, so delta S, and going from 1 to I, is computed as the integral from 1 to I of ds, which in this case would be the integral from 1 to I Cp over t dt. All right, now in the problem, okay, we're given a value of Cp, okay, and only because in this problem we're given a value of Cp that is independent of temperature. So we'll assume that Cp is independent of temperature, that it's constant. So the integral becomes, I pull Cp out, and then the integral of 1 over t dt is just log final over initial. So it should be my, in this case, my temperature of my intermediate state divided by my initial state. Now, okay, one note here before we evaluate this is I have a ratio of temperatures. You need to make sure you're using absolute temperatures. We're given temperatures in degrees C. You need to make sure this is computed in Kelvin. Okay, you need to make sure you're using Kelvin here. Okay, so I'll jump over to MATLAB to actually perform the calculation. Okay, and then we'll write down the result here. Okay, so what I need, so let me write, so my heat capacity in SI, well, 2.4, so not SI units, but kilojoules per kilogram Kelvin. It's the same unit as entropy in the steam tables. So CP is 2.4 on a T1. Okay. T1 is 250 degrees. Okay, but I'm going to add to it 273.15 to convert from Celsius to Kelvin. And then TI, which we're taking to be 800 degrees. Okay. Ideally, it should be slightly greater than 800, but it's as close as we can get. All right, so then I'll write as ds 1i is equal to Cp times natural log of Ti divided by T1. Okay. So log Ti over T1, that's dimensionless, so the units are just the same as Cp. Okay, so if you run this, we get a change in entropy of 1.7244. So Cp, or delta S is 1.7244, and that's kilojoules per kilogram Kelvin. Okay, great. Next, we have an isochoric process in which you go from I to 2. Okay, and so this is going to be isochoric. Now the key is with an isochoric process, okay, for an isochoric process, my first law of balance reduces to delta U is equal to Q. Why? So in theory, it should be delta U is Q plus W, but if we're assuming there's no shaft work and my only work is PV boundary work and my volume's constant, well then that work term is just 0. All right, since dV is 0. So I have delta U is equal to Q, all right, which is equivalent to the integral, in this case from my initial to final state, of CV dt. Okay. Or in differential form, okay, we have the du is equal to dq, which is equal to cv dt. Now my definition of entropy is that ds is equal to dq reversible over t. All right, so this is the change in heat for a reversible process. Okay, so then, from my expression here, all right, I get that ds is equal to, well, dq is equal to cv dt, so dq over t would be cv over t dt. Okay, so then applying, so I have that ds for my isochoric process is equal to cv over t dt. So my change in S, and going from my initial state, or my intermediate state to my final state 2, is the integral from I to 2 of ds, which is equal to the integral from my initial to final state cv over t dt. Now, in the problem statement, we're given a value of cv, which is constant, so I could bring cv out, so I get the cv, then the integral of 1 over t dt, again it's just log, So final temperature relative to initial, in this case is T2 over Ti, the temperature of my intermediate state. Again, I have a ratio of temperatures, so you need to make sure you're using absolute units here. Okay, so then to calculate the change in entropy, okay, let me go back up to MATLAB so we can calculate it. So now we'll have state I to 2, CV, which again is in kilojoules per kilogram kelvins, 1.773. Note that CV is less than CP. For an ideal gas, CP is CV plus R. So we have that. We need our temperatures. So T2 is equal to 400. Okay, but we're going to convert from Celsius to Fahrenheit, so I add 273.15. Ti, in this case, my intermediate temperature, well, I already have it up top, it's Ti. So ds, call I2, is equal to CV times log. Now my final state is state 2 divided by Ti. So the change in entropy for the second process is negative 0.8269. So this is, come on, negative 0.8269, and that's kilojoules per kilogram Kelvin. Okay, so then for the total process, okay, so the change in S, so S is a state function, so delta S, and going from 1 to 2 will be equal to the change in entropy and going from 1 to I plus the change in entropy and going from I to 2. Okay. So my total change in entropy will be equal to, so coming up here, so then ds is equal to the ds, I call it 1I plus ds I2. All right, the sum of my two entropies, which I get to be 0.8975. So the change in entropy is 0.8975 kilojoules per kilogram. Kilojoules per kilogram Kelvin. Okay, great. And if you wanted to compare, we could try and compute it directly from here. So let's give it a try. Something called ds table would just be entropy of my final state, which is 7.0813 minus 6.1545. Okay, so just for comparison, if I were to compute it using the tabulated value, I get 0.9268, which is pretty close to the value of 0.8975 we computed with those heat capacity values given. All right, hope that helps. We'll see you in the next problem.